So yesterday, it was all about these pages, if you remember. Just to sum it up, the key content that we discussed yesterday was the idea of pre-computation. So we all understood pre-computation. Pre means before, computation means to compute. So you are computing something before so that you can reap the fruits later on. I mean, very simple example. We took this as the first question of yesterday, where we said that if we have an array containing some elements, let's say 2, 1, 0, 4, 6, 9, something like this, and then somebody is giving you queries, and every query is of this form, I comma j, where I and j are index, and you have to tell the sum from index I to index j. So let's say this is your index I, and that is your index j. And if you have to give this sum from here all the way till here, then we realize that if we have pre-computed the cumulative sum is just the prefix sum. So if I know what is the cumulative sum starting from here till here, and what is the cumulative sum starting from here till here, then I can just subtract this sum from that sum, and our job will be done, right? So you can clearly see here that the sum from here to here is the sum of 2, 1, 0, 4, 6. So you would write it like 2 plus 1 plus 0 plus 4 plus 6. And from here, if you subtract this much of sum, what are you subtracting? You are subtracting 2 and 1. So you end up getting 0 plus 4 plus 6, which is the sum of this much part. So that was the idea. So we basically, brought in a notion here where we ended up saying that, hey, let's write it in this manner. Let there be something called as PS of I, which is nothing but prefix sum, which is sum of elements from index 0 to index I. So if this is what we have pre-computed, then I can say that sum of the segment from I to j can always be written as prefix sum at j minus prefix sum at I minus 1. That is what we have done here, right? Prefix sum till j, which is this point, will be this much of sum. And if you subtract from here, prefix sum I minus 1 is this, given this is your I, then this much part will be subtracted, and what you will get will be the sum of this chunk, which is from I to j. So this was the basic idea. And now it means that I can answer every query in constant time. So if somebody is asking me that, hey, give me the sum from I to j, I'll just compute this value, which I can compute in order one time and return it, and then the job is done. Right? Okay. All of you recall this concept, and all of you, those who are not there, you kind of connect to it. Can you just type in yes or no, if that's the case? Yeah. Okay. Awesome. So today what we are going to do is we are just going to extend our knowledge in two dimension. See, in computer science, it happens a lot. You learn dynamic programming in one dimension, then you learn it in two dimension, then you learn it in three dimension. That is how you go, right? So this is not dynamic programming. This is just simple pre-computation. Yeah, it can be thought of like that, but for now, let's use the word pre-computation. You'll realize when I talk about dynamic programming, you will realize that there also pre-computations are involved. But here, when I'm saying I want to extend this knowledge to two dimension, what is the kind of problem statement that I am throwing at you? Let us first face that problem statement, and then we will talk ahead. Okay. So those of you who are wondering what we are going to do in this session, this is what we are doing in this session. Let's focus on this session for now. You will have your answer in a span of 10 to 15 minutes if you are aware throughout. Yeah. So problem in two dimension. How can a problem in two dimension be stated? So think of it in this manner. Let's say now you have a two-dimensional array or matrix, whatever you want to call it. So let's take a quick example. So let's say this is your matrix and it contains some values. So let's say 2, 1, 0, 2, 1, 3, 4, 6, 7, 1, 2, 1, 1, 0, 1, 1, something like this. Okay. And now every query that has been given to you is of following form. So you have been given I1 comma J1 and I2 comma J2. I1 comma J1 is coordinate of some cell. I2 comma J2 is coordinate of some other cell. So let's say I1 comma J1, which is given to you, is, let's say for now 1 comma 1. Okay. And I2 comma J2, let's say this is 3 comma 2. Right? So 1 comma 1, which cell is 1 comma 1? I can clearly see this particular cell is 1 comma 1, right? And which is 3 comma 2? So 0, 1, 2, 3, 3, 0, 3, 1, 3, 2. This is 3 comma 2. So what I am supposed to do is, I am supposed to return the sum of this particular submatrix. I'm supposed to return the sum of this particular submatrix. Now, what is the property of this submatrix? That its top left corner is this, which is given by I1 J1, and bottom right corner is that, which is given by I2 J2. So if you try to correlate it with the problem in one dimension, the problem in one dimension used to say that, hey, you have a 1D array, you have a simple 1D array, you have been given index I, you have been given index J, and you have to tell this much of sum, the sum of this subarray. Here the same thing is being told, but in two dimension. So you are given the top left corner and bottom right corner. And you have to focus your entire attention on this particular submatrix. See, if you look at this submatrix, this is the top left and this is the bottom right. So you have to tell the sum of this particular submatrix. So your answer to this particular query, should be the sum of this part. And what is the sum of this part? Can somebody quickly spell the sum of this particular part? Yeah, 3 plus 4 is 7, 8, 10, 11. Very good. So the answer would be 11, right? Okay. So how do I solve it? Let's start with a simple brute force solution. So I'm pretty sure all of you would have an idea of brute force, right? So in brute force, I can simply say that, hey, the easiest thing is to find the sum of all elements contained inside this submatrix. And it is very easy for me to iterate on all the elements of this submatrix, right? Because I can say that, hey, let's consider a bigger matrix, okay? Let's say this is some matrix. And let's say this is the top left and that is the bottom right. So if this particular cell is I1 comma J1, then I can say that, hey, this is row number I1. And if this is I2 J2, then this is row number I2. Similarly, this thing is column J1 and this thing is column J2. So I can just write a for loop where my row goes all the way from I1 to I2, and inside it, in the nested loop, my column goes from J1 to J2. And this can very easily be written in form of nested for loop. So I can just say that, hey, for R equals to I1 to I2, and inside this, for C equals to J1 to J2, I mean J1 all the way till J2, I can say my sum plus equals to matrix of R comma C. And then we can return whatever this sum is. So what does it mean? I mean, this is an absolutely correct solution, but what will be the time complexity of this? Let's say you are answering a query by writing these two nested for loops. How much time would it take? So in the worst case, it would take order of n square time. Yeah. So if you have a n cross n matrix, and let's say your top left was this and bottom right was that, then in that case, you will have to traverse all the cells and it would take you n square time. So each query is being answered in n square time. And if there are q queries, your overall complexity will be nothing but order of q into n square. And this can very easily lead to TLE. So can we do something better? When I say can we do something better, can we do some form of pre-computation? Because see, this question is again that category of question which is throwing a lot of queries at you. And you want to respond to these queries as soon as possible. Instead of running nested n square loop, you want to answer them very, very fast. So what kind of pre-computation should be done here? Like in case of one dimension, it was very easy. We found out the cumulative sum ending at all the indices. What is it that we should do here? So I can see that some of you are suggesting the idea of prefix sum. Then here we should think that, hey, what is prefix sum for us? In this case, what is the idea of prefix sum? I mean, in case of a one-dimensional array, prefix sum at any index was the sum from 0 till I. Here, what do I mean by prefix sum? What to call as prefix sum, basically. So for that, let's take a very simple example. What I'll say is, let's say you have a matrix containing some values 2, 1, 3, 1, 1, 2, 1, 3, 2, 1, 0, 1, something like this. Okay. Now, I would say that, hey, here the idea of prefix sum can be little different. So I would say prefix sum at I comma j. Let's say my I comma j is this. Then prefix sum over here should contain the sum of this particular submatrix. So that is just an idea that I'm giving, and we will see whether that is turning out to be useful or not. Similarly, prefix sum over here should contain the sum of this particular submatrix. And prefix sum over here should contain the sum of this particular submatrix. So basically what I am trying to push from here is that prefix sum at any cell is the sum of submatrix whose top left is fixed. Top left is always 0, 0. And bottom right is that particular cell, which is I comma j. Right? So if you go by this idea, if you keep going by this idea, I can say that, hey, the prefix sum at this index should be equal to the sum of this part. Because this is the submatrix whose top left is this and bottom right is that. So what is this sum? What is this sum? 2 plus 1 is 3 and then 3 plus 3 is 6. So basically the value over here, the prefix sum over here should be 6. Similarly, the prefix sum over here should be the sum of these values. That is what I want. Now, let's say I want to transform this matrix into that sort of matrix. Into that sort of matrix where at any particular index, I have the sum of submatrix whose top left is 0, 0 and bottom right is that index. Then how can I go about it? So in general, let's say if your matrix was something like this, 1, 2, 1, 2, 1, 1, 3, 1, 2, something like this. Okay. Then I want it to get transformed into a prefix sum matrix. So can you tell me the values inside it? What should be the values inside it? Yeah, the value over here should be 1 because the prefix sum at this point is the sum of this part only. And the sum of this part is 1. The prefix sum at this point should be the sum of this part, which is 3. The prefix sum at this point should be the sum of this part, which is 4. Similarly, over here should be the sum of this part, which is 3. And over here, the sum of this part, which is 6. You can go on. What should be the prefix sum at this point? The sum of this part, this entire part, which is 4 plus 4, that is 8. And over here, what should it be? it should be the sum of this part, which is 6. Over here, the sum of this part, which is 3 plus 3 is 6, plus 4 is 10, if I'm not wrong. And over here, the sum of entire matrix, which is, I think 4 plus 4, 8, and then 10, 14, right? So this is what you have. I want to create this kind of matrix first, and then it will probably help me to answer the queries very fast. And that was the idea, right? We wanted to answer all the queries as soon as possible. So the assertion that I'm giving is that if we transform this matrix into this, it will be very easy. So first, let's talk how we can perform this transformation. How can we achieve this transformation? So the idea is very simple. We already know how to compute the prefix sum in a one-dimensional array, right? So now think of it in this manner. Let's say somebody has given you a matrix containing these values. Let's say A, B, C, D, E, F, G, H, I. So initially what you do is you take prefix sum in every row, just in every row. So you treat this row as if it were an independent array, and you take prefix sum in this. Similarly, you treat this as if it were an independent array. This also as if it were an independent array, and take prefix sum in all the rows. Just keep doing that. So if you take prefix sums in this particular row, it will give you these values. You will have A plus B, A plus B plus C, D, D plus E, D plus E plus F, G, G plus H, G plus H plus I, right? Now, just hold on. Now, if you take prefix sum in every column, so what I mean by that is treat every column as if it is an independent array. Treat every column as if it is an independent array, and take the cumulative sum. Take the prefix sum from top all the way till bottom. Then let's see what is going to happen. So I'll draw it a little larger this time. So yeah, let's say you are taking prefix sum in this column. What will be the values you will get? This is just A, and the sum from here to here, it is A plus D. And the sum from here till here till here, it is A plus D plus G. And how about these values? A plus B, and then A plus B plus D plus E. And here you will have A plus B plus D plus E plus G plus H. And here you will have A plus B plus C, then A plus B plus C plus D plus E plus F. And here you'll have the biggest one, which is A plus B plus C all the way till I, right? Now here, can you see one thing? What is the value which you wanted over here? The value which you wanted here was actually the sum of these elements, which is A plus B plus D plus E. Is that what you have gotten here? The answer is yes. Similarly, what is the value which you wanted here? You wanted the sum of these elements, which is A plus B plus C plus D plus E plus F. Is that what you have gotten here? Exactly. Similarly, what is the value that you wanted here? You wanted the sum of these elements. And is that what you have gotten here? The answer is yes. Is that making sense? That just by taking one round of prefix sum in row and another round of prefix sum in column, what we have gotten is what we really wanted. Okay, you know how to compute prefix sums, right? Prefix sums, I mean, you can compute it very easily. In a single row, we have computed prefix sum. I mean, the sum from here to here is A, sum from here to here is A plus B, sum from here to here is A plus B plus C. We did this in all the rows, and then we did that in all the columns. And after that, we realized that the value at any cell is equal to the sum of this submatrix, whose top left is 0, 0, and bottom right is that particular cell, right? So that's the entire idea. Now, see, once you have gotten this thing, you should also think about it that, hey, why did it help? I mean, why did it so happen that taking one round of prefix sum in row and another round of prefix sum in column got the job done for us? Our main idea is to answer the queries as soon as possible. For that, if you remember, I told you that we want to build prefix sum at ij in such a way that it gives the sum of this submatrix. If this is ij, it gives the sum of this submatrix. That was what we wanted, and that is what we are doing. Okay, so we are on that track. And now, if you try to, contemplate that, hey, why doing this thing got us the answer? I mean, got us the prefix sum starting at 00 and ending at ij, then the answer to that is very simple. So guys, let's say you have a matrix. So let's say you have this matrix. Now, let's say if you have taken prefix sum in every row. So the value over here would be equal to the sum of these values. The value over here would be equal to the sum of these values. The value over here would be equal to the sum of these values. The value over here would be equal to the sum of these values. Now, the moment you take prefix sum in every column, what happens? The value over here would be equal to the sum of all these, these, and that. And what is it? It is nothing but the sum of this particular submatrix. So that is what happens. If you take prefix sum in every row, then all these, prefix sum values, they trickle at some point. They trickle at some point. And when you do prefix sum in that column, all those values trickle down at a point, and that way it kind of reflects the sum of this particular submatrix. So this is the reason this particular approach worked. I mean, what was the approach? Just take prefix sum in every row and then take prefix sum in every column. Now, how is it going to help us to answer all the queries very fast? So let's focus our attention on that. Let's say you have a matrix, and now let's say somebody has asked you that, hey, get me the sum of this submatrix whose top left is this and bottom right is that. Okay, so it's our intention to find the sum of this particular submatrix. Okay, now how do I find it? So think of it in this manner. After you have done this pre-computation, what would be the value stored over here at this cell? The value stored at this cell would be equal to the sum of this particular submatrix. Yes or no? You can just keep on replying so that I can see if you're in sync. Yeah. Okay, good. So the value stored over here will be the sum of this big submatrix, right? Now, I want to remove certain parts from here because my intention is to just find out the sum of this part. If my intention is to find out the sum of this part, I must subtract some items from here. So what is it that you would want to subtract? So if you carefully look at it, you would end up realizing that, hey, I want to subtract the contribution of this part, right? And I also want to subtract the contribution of this part. And let me tell you, it is not very hard to do so. Why? Because think of it in this manner. What will be the value which would be stored over here? The value stored over here would be nothing, but it would be the sum of this particular submatrix, right? Similarly, the value stored over here would be the sum of this particular submatrix, correct? Now, if I know it, I can say that, hey, the value stored over here, if I'm calling that as x, then x is this much of sum. And if I am calling this as y, then y is that much of sum. So let's subtract x minus y. And if the value stored over here is this much of sum, then I want to subtract this thing also. Let's call it z. Can I say this will be our answer? Can you say that, hey, this is the sum of the submatrix that we were looking for? Is it right to say so? So at first glance, it might feel like, hey, this is right. But if you look really carefully, no, this is not right. Why? Because this area, this little area has got subtracted 2 times. First, when you subtracted this value, which was y, you subtracted this entire region. So it got subtracted once. And when you subtracted this, which is your z, this region got subtracted again. So we need to bring it back once. So I can say that, hey, the value stored over here at this particular point would be equal to the sum of this part. And if that is w, you can just add w, and that will be equal to your answer, which is the sum of this particular part. So see, what did we end up realizing? We ended up realizing that we can very easily figure out the sum of this particular part if I know the value stored over here, which was my x, which was this huge sum. And if I know the value stored over here, which is this sum. And if I know the value stored over here, which is that sum. And if I know the value stored over here, which is this sum, all these rectangles that I have shown you, they are having their top left at 0, 0. And because their top left is at 0, 0, so certainly the value stored over here would be the sum of this particular submatrix, given we have performed this particular precomputation. So it means that given this precomputation is done, we can just do plus minus of these 4 integers and we would have our answer with us. So that is the key idea. So that was all about it. Now, initially you might be wondering that, hey, why we are taking prefix sum and then suffix sum, and why did we even come up with this sort of definition? Why top left is fixed at 0, 0? And now, if you have really listened to everything that I have said, you can connect all the dots, right? So now what we'll do is, see, it's very important to generalize everything that we have done. Because if you do not generalize, you do not get a formula. If you do not get a formula, you cannot write the code corresponding to it, right? So you need a formula. So let's create a formula for this. And it is super easy to do that. Some of you can do it on your own. So guys, the first step is to do precomputation. So you will precompute. How to precompute? We have already learned that. Where? Here. Prefix sum in all the rows, prefix sum in all the columns, and your precomputation is ready, right? At this point of time, your matrix of I comma j is denoting the prefix sum ending at I comma j. I mean, if this is I comma j, then this much of sum is located over here. We know that. Okay, now move ahead. So what will be the next step? So just to draw this diagram once again, let's say this is your I comma j, I1 j1, and this is your I2 j2. Okay, this is the sum that you are interested in. This one, this part, you need to know this sum. Okay, let me just write, this is I1 j1 and this is I2 j2. So how can you write? You would say that, hey, x, what is x? So x is basically nothing but the value stored over here. The value stored over here would be matrix of I2 j2. From here, I want to subtract something. What is it that I want to subtract? I want to subtract the sum of this particular part. The sum of this particular part would be stored at this index. Can you tell me what is this index? Your answer should be in terms of I1 j1, I2 j2. So if this is your row number I1, what is this row? This row is I1 minus 1. And if this is your column J2, then of course this is, what is this? This is nothing but I1 minus 1 comma J2. Exactly. So this particular cell is I1 minus 1 comma J2 because this cell is at J2 column and this is in the same vertical line, right? So this minus M of I1 minus 1 J2. We need to subtract more, right? We need to also subtract the contribution of this particular part. The contribution of this particular part, which is the sum of this part, would be stored over here. And what is this index? Yeah. So most of you are right because this cell is at row number I2. So of course, this is row I2, right? And if this column is J1, then this column will be J1 minus 1. Yeah. So this thing is effectively I2 comma J1 minus 1. So it will be written as minus M of I2 comma J1 minus 1. Now we all know that this poor area, this little poor area has been subtracted twice. So we need to bring it once. What will this index be? It is very easy to answer because this is I1 J1. So surely this will be I1 minus 1 comma J1 minus 1. Very good. So it can be written as M of I1 minus 1 J1 minus 1. So this is the formula which can instantly give you the sum of this particular submatrix whose top left is I1 J1 and bottom right is I2 J2. Okay, so overall, what does it mean? It means that if we are asked to solve this question, we will first do precomputation. What will be the time complexity of precomputation? How much time does that take? It's super easy. First, you have taken prefix sum in all the rows, and then you have taken prefix sum in all the columns. So taking prefix sum in all the row is very easy because you just want to say that, hey, the value over here should be equal to this plus that. The value over here should be equal to this plus that. So it's just like cumulative sum, right? So you can do that in m into n time, right? Similarly, this thing can also be done in m into n time. So 2 times of m into n, which is effectively m into n only. So pre-computation cost is m into n. And every query is answered in order one time. So if there are q queries, all of them will be answered in order q time. So my total runtime is pre-computation time plus query phase time, which is order of m into n plus q, which is way better than order of m into n into q, which was the initial time complexity. All of you can understand it, right? Okay, so there is even, in fact, a question which is pretty much related to it, and that question can be found on lead code. So let me just show that question to you. So see, here in this question, they have created a class, okay? Now inside this class, there is a constructor where they have passed uh, a matrix, right? And then they are asking a lot of queries. So every query is of form row 1 call 1 and row 2 call 2, where row 1 call 1 is the top left and row 2 call 2 is the bottom right. So see what I have done. So when the constructor has been invoked, I have created a copy of this matrix because you can see this variable here is, a local variable. So I have created a copy of this. I'm keeping a vector of vectors so that I can reference it here in this function. Okay. And then this is equal to the number of rows and n is equal to the number of columns. And then I have called a precompute function. Precompute function is super easy. It is doing some bit of stuff over here. It's doing it little differently. Let me show you the solution that corresponds to what we have discussed. So you can see that prefix sum is being first taken in rows and then in columns. So prefix sum in rows, what is it that we are doing? Nothing. We are just iterating all the rows, and in every row, let's say in ith row, we are saying that prefix, the sum till here plus equals to sum till the previous point. I mean, this is what you do, right? When you take the prefix sum, then at jth point, you say that the value will be equal to that value plus the value which you had at j minus 1th point. This is how you take prefix sums. This is how you took prefix sums even yesterday, right? Similarly, prefix sum in column, I mean, whatever you did in rows over here, the same thing is being done in the columns, right? So we are saying that starting from 0th column, we are iterating on all the rows now, row 1 till row m minus 1. And now here we are saying that the sum till ith row will be added to the sum till I minus 1th row, which is just above it. So after you have invoked both the functions, your prefix sums would be ready. After your prefix sum is ready, the job is pretty easy, because here this much of code that you are seeing is just that formula. But I have written that formula little carefully. In fact, I have to be careful, because if you remember in that formula was this thing minus this thing. Now we are doing a minus only, but we have to be little careful, because this index row 1 minus 1, it could be negative also. Just think about it. Let's say if your row 1 is 0, in that case this would be negative. So, and if it is negative, that means that part would not exist. That upper part which you subtracted would not exist. Just try to reason it. So I added this check that if this thing is greater than equal to 0, that means it exists. So I'll subtract its contribution. Similarly, if this thing is greater than equal to 0, then the other side, which is towards the left, which we wanted to remove, that exists. So we will subtract its contribution. And if that diagonal side, which was common to the upper one and the left one, which you removed, if that exists, if row 1 minus 1 is also non-negative and column 1 minus 1 is also non-negative, then we will bring it once, which is we will add. So we are adding it once. And if you look here and here, we are subtracting. So this thing is like your X, and this thing is like your Y, and this thing is your Z, and this thing is your W. So I mean, whatever I had written, and then you can return your answer. So you can clearly see that the time complexity of this function is order 1. There are just few additions and subtractions which are happening. So every query is indeed being answered in constant time over here. Are we taking another matrix or performing? See, we could have done this thing on top of same matrix itself. If the reference to that matrix was available globally. So here, this matrix, the input matrix, is being passed to the constructor. And because it is being passed to the constructor, there is no way I can pass it over here unless I create another instance variable, another class variable. So I created a class variable so that I can reference it in all the functions, like this function. And then the first line was to first copy the contents of matrix inside this and then perform the pre-computes. Is that making sense? How many of you are clear with the code? Integer overflow, if you're worried about integer overflow, you should first look at the constraints. I mean, what are the different values of uh, you know the cells, and if at all adding them can lead to overflow or not. If it can lead to overflow, you have to take care of that by using appropriate types, long or long whatsoever. Yeah, I mean, I'm a big fan of writing clean code. Okay, so yeah, that's in fact it's important. Whatever if you write code which is clean, you do a favor to yourself as well as to others, because you can debug it fast and others can understand it fast. Okay, so I'm pretty sure that it would have been very easy for you to understand the code. Was it, how many of you understood the code? Okay, all right. So let me tell you what the question says. Whether you have understood the problem or not, you can now look at my screen. The question says that this time you have a 2D matrix, and this is a 2D matrix of characters, okay? So there could be a lot of characters inside it. The easy thing is that those characters are either X or Y or dot, okay? So now you have to find out that how many submatrices are there, how many submatrices are there whose top left is fixed 0 comma 0. So I mean, I'm never going to talk about a submatrix like this. I'm never going to talk about a submatrix like that. I'm only interested in those submatrices whose top left is strictly 0, 0. So I will be interested in something like this. I will be interested in something like this. I will be interested in just something like this or something like this. The important thing is that top left must be fixed, which is 0, 0. So how many such submatrices are there whose top left is 0, 0 and they contain equal number of x and y. So the count of x should be equal to count of y. And this count should be positive. That is also another thing that question says that, hey, how many such submatrices are there in which the number of x and number of y are equal and number of x is not equal to 0. It is some positive quantity. So for instance, you can take some easy examples. Okay, can you see some submatrices over here which are starting at 0, 0 and are having equal number of x and y? Yeah. Okay, let's find some of them out. Can this be one of those? Is this a valid submatrix? Yeah, I think exactly yes, right? Because this submatrix, it is having its top left at 0, 0 and the count of x is 1 and count of y is also 1, right? So this is totally all right for me. Okay, guys, how about something different? How about this? Is this submatrix also okay for me? Why it always have to start with 0, 0? Because that is what the question is asking for. We have not put this condition. Read the question. Question has put this condition that we are only interested in the submatrices which are starting at 0, 0. Okay. Yeah. Okay. So what we were talking about, we were talking about this particular submatrix. In this submatrix, the count of x is 2 and the count of y is also 2. Very good. So this is also a valid submatrix. Now you can take some other example if you'd like to. Let's take this. How about this? Is this all right for me? No, because how many x it has? It has 2x. And how many y it has? It has 3 y's. So the count of x and y are not same. They are different. So this is not the submatrix which I should account for. So yeah, I believe now all of you understand what the question is. It's super simple. It's just asking for how many such submatrices are there which start at 0, 0 and have equal number of x, equal number of y. And the important thing here is that the number of x should be positive. See, at the end of the day, what is it that we want? We want that at any particular cell, let's say we are talking about this cell. Okay. So in this particular submatrix, I want to know what is the count of x and what is the count of y. That's all that I want to know, right? Now, if somehow at this particular point, I am able to store the count of x in this part, the count of x in this prefix submatrix, and the count of y, then the job will be done, right? And it is super easy to do that. It is super easy to store that how many x are present in this part. Similarly for all the cell, for each cell, for this cell also, I would want to store that how many x are present in this part, in this submatrix. And it can very easily be done by using the same approach that we just discussed. And this exact same thing can be done for y also. So do it for x, do it for y, and then just check whether the count of x and count of y at a particular location are equal or not. And on top of that, just put one more condition that that value should be positive. And it will be super easy to do it. So let's say you had a matrix which looked like this, contained x dot y, y, x dot x, something like this. Then I would say that, hey, let's do one thing. Let's build a 3 cross 3 matrix, okay, where initially all the values are 0 And now we want to first take prefix sum in every row. And we are doing it for x. Okay, we are doing it for x and we will take prefix sum in every row. So what will we end up doing? So we will say that, hey, I have got an x over here. So this value should be changed to 1, right? And now I have got a dot over here. Because I've got a dot over here, so I would not do plus 1 over here. But because I am taking prefix sum, so the value over here will be equal to this plus that. So we will get a 1. Now over here, I have an x. So for x, I will do a plus 1. And because I'm taking a prefix sum, so the value over here will be 1 plus this, which is 2. So you can see that the value stored over here is containing how many x's are there in this part. The value stored over here is containing how many x's are there in this part. The value stored over here is containing how many x's are there in this part. The same thing for the next row. Do the same thing for the next row. You'd say that, hey, this is a dot, so this will continue to be 0. Now here it is a y, so it will be 0, 0 plus 0 will be 0. Similarly here also 0. Now if you do it for this row, you would say that, hey, it is an x here, so this thing will become 1, right? And then because it's a dot, so 0 plus 1, 1, 1 plus 1, 2. So basically you have done it for x in row. Now you can do the same thing column. You can take the prefix sum column wise also. So if you take it column wise, let's see what is going to happen. So you will get values 1, 1 and 2. So this is 1, 1 and 2. And here you will get 1, 1 and again 2. And here you will get 2, 2 and 4. And you can see that the value stored over here should ideally have been equal to 2 because there are 2 x's, and that is exactly the case. The value stored over here should represent how many x's are there in this, which is 4, and that is exactly the case. So guys, it is very easily to craft this matrix. And similarly, you can create, so call this matrix as prefix matrix for x. In the exact same style, you can craft another matrix, which you can call prefix sums for y. And you can create both these matrices in order m into n time. And then you just need to write a for loop. You just need to write a for loop for I equals to 0 to m minus 1 and for j equals to 0 to n minus 1. And what is it that you need to check? You just need to check that if prefix x ij is equal to prefix y ij, then what does it mean? It means that at I comma j, let's say if this is I comma j, it means that at I comma j, whatever is the count of x, the same is the count of y. So basically in that submatrix, the number of x and y are equal. And for that, I can just clap and do count plus plus. And finally, return that count. There is just one thing that we will need to probably take care of. Can you tell me what is that? So if you remember the question said that the count should be positive. The count should be positive. Yeah, at least 1, right? See, certain times it can very well happen that you have an input like this. If you have an input like this, in this matrix, what is the count of x? 0. What is the count of y? 0. But you don't want to take this into account. So you have to put one more check. You can put that on your own. You can put an AND condition, and that AND condition will be followed by a check that this value must be positive. So if this value is positive, and on top of that, if this is equal to that, we'll do count plus plus, and then the job is done. Yeah. Okay. So how many of you understood this approach and can code this problem now on your own without seeking any external help, especially ChatGPT or anything else? Rather than computing for x and y separately, we can find count x. See, there are some approaches. Let me discuss some alternates. You will, and some of you have talked about those alternates, I guess. We can also do one thing. We can, yeah. So good. It's good that a lot of you are able to come up with some uh, solutions which sound pretty interesting. So there is one solution that I have got from one of you. I'm not sure who exactly commented this, but that's very good that you guys are, so fast learners. You're able to catch all that I'm saying. So see, what one of you said is very simple. He said that, hey, let's do one thing. No, replace every x by +1, replace every y by -1, and replace every dot by 0. Did it click? That's such a great idea, I would say. Because whoever gave this approach, whoever proposed this approach, he said that if, let's say, this is your matrix, and you have got x dot y, x dot y, x dot x dot, then guys, if I transform this matrix using this rule, that I want to substitute every x with 1, every y with -1, and every dot with this, what will I end up getting? So it'll be 1 0 -1 1 0 -1 1 1 and 0 0 1 0. Guys, now you can clearly see that the sum of this submatrix is 0. Why the sum of this submatrix is 0? Because it contains one instance of 1 and one instance of -1. And because every y has been replaced by -1 and every x has been replaced by +1, so if any submatrix sum is 0, that means it contains equal number of +1 and equal number of -1, which means equal number of x and equal number of y. Does that make sense? How many of you now clearly get this? Yeah, you have a very good question here, that what about the case of at least one x? At least one x. This is a food for thought, which I would leave you to think. See, this is a very good approach. Whoever suggested this approach, I comment that. But now you also think that how would you account for, because see, I mean, if this would have been the case, still the sum of this part would have been 0. I mean, the value over here would have been 0, but you don't want to take this, right? So how would you, uh, you know, uh, get rid of those submatrices which do not have any x at all? So just think about that. Yeah, you can very easily come up with a, just one or two extra lines of code which will take this into account, and your job would be done. Cool. So did you, I mean, okay, so before we proceed ahead to something else, in fact, see, I taught you how to perform pre-computation in 2D. So that idea is clear to all? Pre-computation in 2D, right? Okay. How I taught you this thing is, given a matrix, you just do prefix sum in every row. This matrix becomes matrix dash, and then do prefix sum in every column. This matrix becomes matrix double dash, and this is what your answer is. Here you are doing it in two pass. It's two pass, right? Because first, you are writing a nested for loop to do prefix sum in every row, and then you are writing another nested for loop to do prefix sum in every column. Can we do it in a single pass? So there is a way to do it in one pass also, and that is very much useful. That will expose to you a little different concept. In fact, we have already covered it, but probably I can give it a different name this time. So just look at it. Okay, this will be the last thing which we'll cover for today. See, let's say this is your original matrix. What is the value that you want to store here? You want to store over here the sum of this particular submatrix, correct? Now, just tell me one thing. If you know what is the value present over here, let's say the value present over here is x, and let's say the value present over here is y. Can you quickly compute the value present over here? Given that you know x and y, can you compute this value? Just think about it. So let me show it to you. X is the sum of this particular submatrix. Similarly, y is the sum of this particular submatrix, right? So if I do x plus y, what is wrong with it? Let's say I do x plus y. We all know that, hey, this thing x is the sum of this part, right? And this thing y is the sum of that part. So what is wrong with it is this common area. Very good. The wrong is this common area, because this common area came when you added x, and this common area came when you added y. But I can very easily subtract it, because if the value stored here is z, and if I do x plus y minus z, I can clearly get rid of that area. And on top of that, if I add the value present here, let's say the value present over here was matrix of I comma j, and this exactly is the value of matrix of I comma j. That's it. So this is simple approach of inclusion exclusion. When you include one area and then another area, something is repeated, and then you remove that. We have already done that while answering the queries. We have done that, and this is exactly inspired from there. So, if I have to write it down in terms of a formula, I would say that, hey, the, matrix of ij will be equal to the value stored over here, which is matrix of I minus 1j, plus the value stored over here, which is matrix of ij minus 1. And we all know that this thing has come twice, so we need to subtract it once. So we will do minus of matrix I minus 1, j minus 1. And to this, we will add whatever is the actual value, the original value stored over here, which is matrix of ij. So using this formula also, you can get your job done. Is it making sense? How many of you are able to understand that this thing also will lead to the same pre-computation happening, but in a different style? Just the style is different, but the output is going to be exactly the same. You just have to take care of indices, because for some I comma j, I minus 1 might be negative, j minus 1 might be negative, or both might be negative. So you just have to take care of these things, and then your job would be done.